My name's Max, and my talk is going to be a little bit about game theory and machine learning algorithms. We're just going to kind of go over the basics, go over a little bit about what game theory is. At the end of the call, if somebody wants to talk about specific algorithms or code and things like that, or an idea on how you'd implement it, we can do that. But this will just be sort of a little primer. Okay. Most people have seen A Beautiful Mind. Game theory started around the 40s. A guy named von Neumann was the guy who actually originated it, or kind of defined it. And John Nash is sort of the one who formalized it with his Nash equilibriums. And you've probably seen the tables around. Maybe you have, maybe you haven't. But if anyone remembers Beautiful Mind with like the 4 females and like the cooperation game, that was not a Nash equilibrium at all. It it actually is, a lot of economists are pretty frown upon that movie, even though it won a bunch of awards, because it was actually the opposite. It was the mixed equilibrium that it's actually not, is the exact opposite of a Nash equilibrium. So I'm going to go into a classic example of how you model a Nash equilibrium and what it actually means. Has anybody ever heard of the prisoner's dilemma? Just anybody?
Heard of it, but I don't know what it is.
Yeah, so it's prisoner's dilemma is one of the most it's what you first learn in like an intro to game theory course, where they're just sort of trying to explain what a Nash equilibrium is. And so if you look at, can you see my cursor?
Yes.
Yeah, so what you see is you have 2 players. In this case, the players are both prisoners, and they've committed a crime, and now they're being sort of interviewed by the police, and they have 2 options. So prisoner 1 can confess or not confess. Prisoner 2 can confess, not confess. It's a uniform game, meaning both players have the same 2 options, but they're isolated. So they take the 2 prisoners into 2 rooms, and they both have to choose for themselves which option they prefer. So you can see if they both confess, they both get a -6, so they both go to jail, effectively, or for a longer time. If you look at the outcomes, the optimal outcome, like the one where the prisoners actually do the least time, is that both of them don't confess. If they both don't confess, the police don't really have much evidence on either of them. And then there's the 2 uniform ones, where if player 1 does not, or basically if they rat on each other, and the other one doesn't confess, then they get their optimal payout. So player 1 in this this square, we get a 0 payoff. Player 2 get a 0 payoff here. So these are just sort of like the matrix and how you model it. Does anyone sort of have any questions about like what this means? Player 1 has the strategy here. Its payoff is always first. Then player 2's. Is this making any sense?
Yes, it is.
Yeah.
Okay. So what the Nash equilibrium is, basically, a Nash equilibrium is you make a choice where you have no reason to deviate. So the prisoner's dilemma is always taught initially because if you are player 1 or you're player 2 and you don't know what the other person is doing, you always have an equilibrium of confessing, because your payout of confessing versus not confessing, let's just take these choices. Confessing gives you a better payout here, and it gives you a better payout here. So both actual prisoners, prisoner 1 and prisoner 2, have a dominant strategy. So they're always going to get the optimal payout by confessing if they don't know what the other player does. So how do I back up? So it's kind of counterintuitive, but if each player is taken in isolation, they actually have a dominant strategy to confess. So the Nash equilibrium of a prisoner's dilemma is confess and confess right here. And it's called the prisoner's dilemma because if both of them, stay still, don't say anything, it's best for both of them. But because they're in isolation and they're choosing independently, the Nash equilibrium is for both players to confess. Is everybody set? Is that making sense?
Yeah.
Okay, so that's sort of the simplest example of a Nash equilibrium, and there's a lot of games that are modeled by 2x2 Nash equilibriums. But the prisoner's dilemma is nice because there is a dominant strategy. Player 1 and player 2 both will confess in every case. They have no incentive to deviate, and you end up with just one equilibrium. You can have multiple equilibriums and mixed equilibriums, and you can have many players, which actually go out into multi-dimensional, which are modeled in a totally different way. But this just kind of gives you a primer that in a Nash equilibrium, no player has a reason to deviate. And if they do have a reason to deviate, it means that it's a mixed equilibrium. The classic mixed equilibrium is rock, paper, scissors. The optimal mixed equilibrium is to throw rock, paper, and scissors randomly 1/3 of the time. So, let's see here. So there's other types of games. The ones that computers are best are what are called induction games. So there's sequential games. So the Prisoner's Dilemma was a simultaneous game where both actors act independently, but they act at effectively the same time. So the decision is made at a uniform point of time, and timing doesn't really matter. Computers are a whole lot better at a sequential game. Chess is the classic one. This is most machine learning guys. I'll try to get a computer to beat the grandmaster of chess, and up until about 20 years ago, only the best ones could beat a grandmaster of chess, and it took like months and months of computer time to learn. These days, a typical desktop computer with the right algorithm can take about a half day and can beat all the best chess players in the world. But the idea for a sequential game like this is basically you have to survey the entire amount of moves that can be made, and basically choose between a tree of moving all your pieces and whatever can be made at a given scenario and choose the best outcome. I think I heard that most chess simulations get somewhere, they do about 150 moves ahead of every situation and then prune the tree on what's the best option, and then they make their decision. If you think about a chessboard, what's a chessboard? 8x8? 10x10? 12x12? I don't know. There's 150 moves in the future. You're starting to count into the hundreds of millions every move of each option, and you're just kind of trimming out moves that are suboptimal very quickly and getting to the set of possible moves that may be optimal, and then you're kind of doing that. So this is just a simple way that you can view an induction game. Basically, you have it doesn't really matter what these decisions are. It's just basically showing you that there's payoffs at the bottom here, and based on these two sets, player 1 chooses first, and player 1 sees that their payoff are 1 and 3 or 4 and 3. So they have a dominant strategy to go right. So this whole left side is going to be removed because player 1 would never choose it. And then based on that, player 2 would choose their best strategy. So the actual sequential endpoint of this 2-level tree is player 1 gets 4, player 2 gets a 2. And so there's a lot of these trees that happen, and they go down through these trees that grow exponentially, and the payoffs in chess are normally either the type of piece, like has a different point measure, or there are strategies for actually what positioning and like how, whether you're playing offensively or defensively. I don't know, I'm not that good at chess. But there's all sorts of algorithms that I had to learn for a game theory course that was very, very rigorous and obnoxious. Okay, so how do machines actually learn based on these induction games? There always has to be a feedback loop for any game theory set. So you can solve all sorts of games. You can solve card games, you can solve auction games, induction games. You can model a lot of complex business situations, but what you need is a feedback loop. So a feedback loop is as simple as with a given input, are you going to get a good outcome or a bad output? In chess, you can have points per piece, or you can just have the binary, am I going to be in checkmate anytime soon? That can be a simple feedback loop. A lot of the better ones are the ones that have a gradient. So do we have a lot of card players on here? Anybody?
A little bit.
Yeah, a little bit. Okay. So like the common one that I've been working on recently is euchre, just a bot to play euchre. So there's how many tricks you can take, the estimated amount of tricks you can take, your partner can take with the face card up. So you actually have like a gradient. You play the hand, you run through random card games a million times, and you actually have this feedback loop of, in this situation, what should you call? Should you call or should you pass? Like that sort of thing. So the more options you have and the more feedback you have that's gradiented out to like different types of feedback are normally easier games and quicker games to solve. The problem that I've been doing for a client recently, you guys all know about Uber and Lyft, right? That's obvious. Well, Uber and Lyft, their big contribution and the reason that they have so many data scientists is because Uber and Lyft are very good at predicting where a driver should be and which driver should pick up a certain person, and also what their supply and their demand are going to be. Beyond that, Uber and Lyft have taken their data that's basically hundreds of millions of rides and decorated all their data with 50 to 100 variables. Actually, my roommate from college worked for Uber, and he said they had 79 variables that affect the ride's price. So it can be anything from weather, it can be sporting events, it can be stuff that you would not actually expect. Which side of the street, I guess, is a big one. All sorts of things that actually affect the price beyond just the simple supply and demand. And so game theory or machine learning, whatever you want to call it, will take these inputs of all these 79 variables that they've determined attribute to the price, and they will say, okay, based on these 79 variables, there's some level of each of these variables that goes into a formula and determines the price. And then they basically, with every ride, they run through the price, and if the price is accepted by both parties, it's a plus. If they're not, it's a minus. And based on just that simple equation, they say, okay, if we're getting too many pluses, we need to up the price a little bit more, or dampen it, and basically they just keep feeding more and more data into these variables, see if they can find more that reliably determine this price, or they cut them out every once in a while. So there's like a lot of regression modeling. Is that making any sense? You just take a ton of variables, get a feedback loop, and then either add variables or trim them out. Sorry. This gets really kind of technical kind of quickly. But now I need a volunteer because I want to have a simple game. So I just need one of you. Somebody come off on mute and just, if you want to volunteer, and we'll play a simple game. It could be anyone. You don't have to know anything about game theory. It would be better if you didn't.
Well, then I'm happy to volunteer.
Okay.
This is Lindsay.
Yep. We're going to play the ultimatum game. This is
Okay.
a simple game. Okay. So the condition is we have $100 to split. Neither of us own it. So it's not like, we're splitting the game. Like we're splitting $100 between us. Let's say the typical setup is we found $100. We both saw it. We both picked it up, and now we have to figure out how to split it. Now you get to offer me how much to split it, and if I accept it, then we split the $100, and if I don't accept, then neither of us get the money.
Well, I would offer to split it. I would offer to give you $50 and me take $50.
Okay, and I would accept that, obviously. But is that actually an equilibrium?
I don't know.
Anybody else? Anybody else want to take a guess on what you would offer me?
It's been decades since I had game theory in college, but if I'm remembering right, you can do the split where it's slightly in your favor and still get it because they're still coming out ahead.
Correct. So take that a level deeper. So 50-50 is what Lindsay said. You're saying slightly in your favor. What do you think slightly in your favor would mean?
Somewhere between $5 and $10 more.
Okay.
You don't want to get too greedy, otherwise they'll view it as saying punishing you by refusing.
Yep, and that's actually a part of game theory that they've developed recently, which is called chaos theory, because humans don't act rationally like computers. And I'm not saying that they're irrational, like, crazy. I'm just saying that humans have an element of fairness when they make decisions, what they perceive to be fair. Whereas if you were splitting this with a computer, how would you split it?
I mean, I would want it all for me if it was a computer.
Yes, so you'd offer $0 and the computer would reject it.
So maybe like offer them 30 and I'll take 70.
The Nash equilibrium of this problem is not to offer the other person $1.
Huh.
Because they are better off, they get more than 0, and you get the most of the profit. It's actually, if you can split it down to the cent, it's to offer them $99.99. And that's how almost all computers are modeled to solve machine learning problems, is if they are at all better off in a simple problem, they will take that. And the converse, if they can be at all better off and, assume that the other side is rational, then they'll do exactly that. They'll offer $99 or $99.99, whatever it is, if they're playing that sort of game. Now, I think it's Jason, right?
Yes.
So when they actually run this game with 100,000 people, there's a lot of people who won't accept anything but 50-50. Because there's this notion of fairness that comes into these human types of games where fairness is a component in how most people actually make decisions. So a lot of the times, if you run this game and you start with what a computer would offer, a human rejects it every time until you get somewhere around $35. And depending on the demographic or the age or all sorts of different factors, the amount of money, the risk tolerance, that's sort of where a human component is necessary to actually get an equilibrium that's what economists would say irrational, but is actually the right answer. So it's kind of a just kind of an exercise on saying that all decisions, they don't make a decision that says, if I'm better off, I'm going to take it. They really just don't do that. Actually, before I go into this, what other things do humans make irrational decisions about? Irrational in that context.
Before anyone sneaks in to answer that, can I make a note / ask you a question?
Sure.
Next.
Yeah.
Do you think personally that part of the reason that people don't make what a computer would consider a rational decision is because part of our utility function is like future cooperation with other humans?
Well, that's called a cooperation game. So let's change this ultimatum game, and let's say that it's going to happen 100 million times. There's a game called the cooperation ultimatum game where you give me an offer, and if I accept it, then you get another $100 to play the game again. If I reject it, the game's over. So in that case, you never want me to stop playing the game so that we can continue having this sort of game. And in that case, there's a mixed equilibrium. It depends on your time value of money. And there's a probability function on it. But a computer will do anything it can to get you to play the game over again. And then it just depends on which player offers first and what the player will accept. And so it kind of goes back and forth between humans. It's the tit for tat strategy where if you offer me $99 one time, I'll offer you $99 the next time. If I offer you $1 one time, I'll offer $1 the next time. But it normally starts at 50-50 and then gyrates back and forth. There's cooperation games. There's also competitive games, which are the ones that are more interesting to study. Have you guys ever heard of the war of attrition?
Yes.
Yeah. So this one's an easy one. Okay, I am going to put $100 out there, and I want you to bid with each other on how much you would pay for my $100 bill. Somebody throw out a number.
$25.
Okay. Somebody else throw out another number.
60.
Okay. Lindsay?
70.
Okay. Jason?
I'm done.
You're done? You're going to let her have it?
$99.99.
Okay. So Lindsay, you've already bid $70.
Yeah. And I almost had it.
And you almost had it. Now what if it wasn't an auction and it was a style of auction where you had to pay the $70? Then what would you do? So you're $70 in.
Uh-huh.
Jason's got it. If you go to $100,
I got it.
you get it.
But if I don't, I still pay 70?
Yep.
Then
So
I would pay the $100.
Yep. And Jason's already in there for $99.99. And so he would actually overbid you for 101 penny because then he would only lose a penny.
Right.
And you would continue on this path infinitely
Ooh.
because you're always in for more. The only way that you can break that ultimatum game is actually if Jason went to, let's say you bid $100, he would have to go to 201 penny to make you indifferent, just to end the game. You would both lose money,
Yeah.
but typical
Makes me
example of a war of attrition. Does anybody
makes
know?
me anxious. I don't like the ultimatum game.
Well, we're going into a war of attrition. Does anyone know what the most common war of attrition is? I'll give you a hint. It happened about a month ago.
Elections.
Elections. Both sides pay, and they're in. They have to pay either way, but only one side wins. So any game where you're going to end up in a game where only one person's going to win, but you're both going to end up losing some utility, that's a war of attrition. Yeah, there's typical examples, but elections are normally it. Those are all kind of the basic games. Does anyone have any questions so far? Okay. So basically, I've been going through this, already kind of spelled it out. Machine learning is chugging in an input, running it through some function, seeing if your output's better or worse than you expect, ranking it, and then leaning on those variables so that you get a better output rather than a worse output. A card game, chess, all these well-defined games, you basically can run random operations, which is the easiest type of machine learning, where you just do a random operation and see if you do better or worse than you did before. If you did better, you just run that operation again and again and again and a million times, and you just deviate towards a natural equilibrium for one situation. And that's basically it. At a certain level, it all becomes about programming. It all becomes about what languages you use, what kind of memory you use, what algorithm you use. If you know close, like Uber knew that supply and demand determined 85% of their algorithm pretty quickly. But they've been spending millions and millions and millions of dollars lobbying, but also millions and millions of dollars on figuring out those extra variables that can make them more money. So at this point, you kind of go into the programmer space of just don't use an interpreted language. Don't use something that doesn't use strong types. Use primitive arrays if you really want to get into it. Use a language that can actually chunk through hundreds of millions of records. Define your game and just run it as many times as you can. Or start getting into different algorithms that predict the game more effectively, like running through Nash equilibriums and starting from that point. You'll get to the right answer quicker. That's all I had. Just kind of wanted to bring into more of a discussion, any questions about any sort of game theory stuff or any algorithms.